Hi guys, my name is Peter C. Dogba Jr., mathematics instructor at the University of Liberia and your math tutor. In my today's video, I will be looking at matrix algebra, and under matrix algebra, we will be discussing eigenvalues and eigenvectors. So to start with, we have an example that says that determine the eigenvalues and eigenvectors of the below matrix. And now the matrix is matrix A, which is 7, 3, 3, minus 1. Now, we know that there is a particular relationship that exists between eigenvectors and matrices under consideration. So if you have this matrix to be matrix A, then it means that the eigenvector is that vector when multiplied by matrix A. So we call this X the eigenvector. So when you multiply the eigenvector by matrix A, you have a result of a constant, which we call lambda, times the eigenvector. So with this now, we can be able to determine the eigenvector by first determining the eigenvalues. So we further carry on some operation right here. So we send this term across the equal sign. We have ax bar, or a vector x equal minus lambda of vector x equals to 0. So now we can factor out vector x. So you have a minus lambda times vector x equals to 0. Now you have a minus lambda. It's, let's say, matrix A minus a constant 3. So since we cannot carry on this operation, because when we are doing matrix operation, especially matrix addition and matrix subtraction, the dimensions must be the same. If you watch our previous videos, you will learn that better. So if you have matrix A to be a kind of 2 by 2 matrix, like for example 1, 2, 3, and 4, then it means that the next element must be a matrix, and it should also be of the same dimension. It necessarily don't have to be the same elements, but it must be of the same dimension. That is a 2 by 2 matrix as well. So you can have 3, you can have 5, 7, you can have 1, and so forth. But now, since this is not a matrix, this is a constant. It's like having a constant here. So what we can do, we can attach an identity matrix. An identity matrix is almost like attaching 1 to a number. So it's like saying you have 3 divided by 3. So 3 divided by 3 is 1. So we want to attach a kind of identity matrix. And since this is a 2 by 2 matrix, the identity matrix is just 1, 0, 1, 0, 1. So this is an identity matrix. So we're going to attach this identity matrix to lambda, so that we can be able to carry on the operation right within it. So if we do that, we have so we now have, let's take it on this we have a minus lambda times r vector x equals to 0. Now at this point now, we need to be very, very careful, because we know that the eigenvector must be a non-trivial vector. That is, the eigenvector should not be a vector that comprises of all zeros. No, it should not be a 0 vector. So in order to make this not to be a 0 vector, we need to carry on some operation on this expression. We need to bring in some properties that will be able to help us, so that this vector cannot end up in being a non-trivial vector. And one thing we know is that this particular matrix A minus lambda r, if it is linearly independent, then it means that we will have a non-trivial vector at the end result. So if this matrix is a non-trivial matrix, then it also implies that this matrix is an invertible matrix. And when a matrix is an invertible matrix, the determinant of that matrix is equal to 0. So we can find the determinant of this matrix, this one right here. So we use the absolute value symbols, the determinant minus A minus lambda times R equals to 0. So we want to be able to manipulate this equation so that we'll be able to obtain some eigenvalues that will be used to determine the eigenvectors. So let's work with that. We have A minus lambda R. So we collected what is within. We want to deal with what is within first. When we have subtracted this matrix from this one, then we can find its determinant. So to do that, we have matrix A to be this 2 by 2 matrix, which is 7, 3, 3 minus 1 minus, now lambda, we write lambda. Then we have the identity matrix now. Since there is a 2 by 2 matrix, the identity will be a 2 by 2 matrix. If this was a 3 by 3, it's going to be a 3 by 3 matrix as well. So we have 1, 0, 0, 1. Now if we multiply, we have 7, 3, 3 minus 1 minus, so lambda times 1 is lambda, and lambda times 0 is 0. Lambda times 0 is 0, and lambda times 1 is lambda. So what we need to do is that we need to further carry on the last stage of the operation. So it's 7. Now, element by element, 7 minus lambda. So you have 7 minus lambda. 3 minus 0 is just 3. 3 minus 0 is again 3. Then minus 1 minus lambda is minus 1 minus lambda. So now since we've now gotten A minus lambda R, we can now find its determinant, A minus lambda R. So the determinant now would just be this times this one, and this times this one. So this is 7 minus lambda times minus 1 minus lambda minus, because we know the first one is plus and the second one is minus, and it is alternating in that form. So minus this one now is 3 times 3. So if we further simplify, we have the determinant to just be equal to 7 times minus 1 is minus 7. So we have, so now mind you that this whole thing, this entire expression now is equal to 0. So this whole thing here will just be equal to 0. So we can just take this whole expression and avoid now just rewriting this thing. So we have 7 times 1 is minus 7. And 7 times lambda is again minus 7 lambda. Lambda times minus 1, so it's minus and minus is positive lambda. And then lambda times lambda is just equal to positive lambda square. So it's positive lambda square. And then minus 3 times 3 is 9. All equals to 0. So now we can solve for lambda. So we have this to be like 10. We have lambda square to be equal to minus 6 lambda. Minus 7 and minus 9 is 10, 16. Minus 16 equals to 0. So we can see how best we can factorize it. So we can have lambda times lambda, which two numbers we multiply to give us 16. If we add those two numbers, or if we subtract those two numbers, we will get minus 6. So you have 8, 2 and 8. So if we have negative to 8 and positive on 2, positive 2 times negative 8 is negative 16. Positive 2 minus 8 is minus 6. So we have lambda plus 2 is equal to 0, and lambda minus 8 now is equals to 0. So lambda 1 is equals to minus 2, and lambda 2 is equal to positive 8. So we have lambda now to be equal to minus 2 and 8. So these are the two values that we have for lambda. And these values are what we refer to as the eigenvalues. The eigenvalues, or we call them the characteristic roots. Now we call them a characteristic root because this particular equation was the determinant of this expression was the characteristic equation. So leading to this one now, it becomes the characteristic root. So with these eigenvalues, we can now determine the eigenvector. So let's, okay, which one we keeping? We have our, let's maintain this one. Okay, so this was what we got at the end. So we must maintain it. Okay. Okay, now, so we have, we coming back here now, right here. So we have A minus lambda I. Okay, so we just take it from right here. Lambda I times the eigenvector equals to 0. So what is this? What is this? What is this expression? What is this one? What we got right here was matrix 7 minus lambda 3 minus 1 minus lambda. That was what we got. So the reason why we found the determinant was because we wanted to solve for both the eigenvalues. That's what that was the reason why we went as far as finding the determinant. So now if we multiply this now by this vector, which is like x1, x2, now must be equal to, now this is a 0 vector, so we can have 0, 0. Now we have to replace lambda with its value. So since we have two values for lambda, we have to take them one by one. So we can take the first value at lambda equals to minus 2. So when lambda is minus 2, we replace it. We have 7 minus 2. 7 is 7 minus minus 2. So it's plus. So you have 9. Then in the next area is 3. Then this area now is just 3. And this is minus 1 minus minus 2. Minus and minus is plus. So it gave us 1 right there. So now we have x1, x2 equals to 0. So this just indicates that we are dealing with two variables in terms of x1 and x2. So we don't necessarily have to be moving with it continuously. We need to solve for x1 and x2. So we can write a kind of augmented matrix for this. So we have 9, 3, 3, 1, then 0, 0. So our target here now is to rewrite this in the form of row echelon form, thereby making this to be 0, making this to be a leading one, or we can even put it into a reduced row echelon form. It's not really the problem to put it in reduced row echelon form. We can just put it in row echelon form by making this to be 1, 0, 1, right? Because we will not come up here to put everything in that reduced row echelon form. So we can just put it in either row echelon form or reduced row echelon form. We still find the value. But if we put it in row echelon form, we will have this is 3 now. So we need to have a 0 right here. So what we can do is, since we need 0 here, we can say 3, we can say arrow 1, which is 9, minus 3 times arrow 2. So 9 minus, now 3 times 3 is 9. So this will give us 0. So this now, we are applying this on row 2. So we erase this portion. So the first row remain constant. We are not touching anything on the first row. So we have 9, we have 3, and we have 0 right here. So it's the second row that will be a factor. So it is 3, this 9, arrow 1 is 9, minus 3 times this 3 is 9 as well. So this is 0. Now this is 3. So 3 times this 3, as 3 times this 1 is 3. So it also goes to 0. And then this side now is also 0 as well. So what do we observe? Now, we know that this is x1, this is x2. So by way of back substitution, meaning you have x2, you have x1, by way of the back substitution, we do not have a value now for x2. So from the first row, we have 9x1 plus 3x2 to be equal to 0. So since we do not need a 0 vector, we say the eigenvector should not be a 0 vector. So we can select values for x2. Because if this 9x1 is equal to negative 3x2, if we divide both sides by 3, in fact, we will just have 3. Let's say we divide both sides by 9. We'll just have x1 now to be equal to minus 1 over 3 x2. So if we select values for x2 other than 0, we can select, we can say 1, we can say 2, 3, and so forth, but it should not be 0 because eigenvectors are not 0 vectors. So we say let x2 equals to 1, for example. Then we can have x1 to be minus 1 over 3 times 1. So x1 now is equals to minus 1 over 3. So the eigenvalue minus 2 has its eigenvector to be x equals x1 and x2. So what is x1? x1 is minus 1 over 3 and x2 is 1. So we have just found the eigenvalue And from this eigenvalue, we determine the eigenvector for this. So now we need to move back to the second value that we got. What was the second value? The second value that we got was what? Positive 8. So we erase this one. So this now was, the first one was lambda 1. So we now move to lambda 2. So lambda 2 now is positive 8. So we're using the same operation. So we have 7 minus 8 is just minus 1. And then this is 3. This one now is 3. This is minus 1 minus 8 is just minus 9. So we just write the 0 and the 0. Now we must rewrite this in the form of a row echelon form. Just rewrite it, bring in some operations. So we know that we can swap rows. We can swap rows. So since we have 1 year and we need 1 year, in fact, so we can just make this to be a kind of leading one by multiplying it by negative. Better still, we can leave it and focus on the 3 down here. So let's say we attach negative to row 1 to just make this to be a leading one. So that now will lead to positive 1 minus 3, 0. The second row remain the same. So we also apply another operation to make this to be 0. On every leading one, there should be all zeros. So to make this to be 1 now, we can say 3 row 1. 3 times this 1 is 3 minus row 2, which is now 3. It gives us 0. So we indicate that we are applying this operation on row 2. So this will now produce the first row remains the same. You have 1 minus 3, 0. And the second row now, this is 3 times 1, or 3 times row 1, which is just 3. Minus this 3 is 0. 3 times this 3 is 9. So it's minus 9 minus, and then our 2 is minus 9. So this minus and minus will give us positive. So this will just be 0 as well. And then 3 times this is 0. So this whole thing will just be 0. So again, we have x2 to be 0. But because we do not need a 0 vector, so we say we're going to allow x2 to be some other values other than 0. So now we have this one to be x1 minus 3x2 all equals to 0. So we solve for x1, and then we have positive 3x2. So now we can say let x2 equals to some other values. So we say let x2 equal to 1. So x1 now will be 3 times 1. Therefore, we will have x1 to be equals to 3. And then we know that x2 is equals to 1. So our eigenvalue positive 8, lambda 2 is equals to positive 8, produces an eigenvector vector x is equal to x1, x2, and which is now 3 and 1. So this is how we find eigenvalues and eigenvectors of a given 2 by 2 matrix. So in subsequent videos, we will do 3 by 3 matrix, 4 by 4 matrix, so that we have a broader understanding of how to find the eigenvalues and the eigenvectors of matrices.